Let's get started. What we're trying to do is make a connection between quantum mechanics and bulk properties. In other words, thermodynamics. That's the goal. You've all had thermodynamics, and we're used to describing large systems, macroscopic systems like a liter of water, with certain properties. Temperature, for example, might be pressure. We don't, in thermodynamics, worry about the connection to microscopic. We know that physical systems obey Schrödinger's equations of motion, right? And so when we study quantum mechanics in physical chemistry or in physics, we typically deal with a few particles in a very small system, and we calculate the energy levels or the states. Energy level and state are slightly different things, and I think the chapter actually got confused at one point. But maybe they didn't, and I misread it. But in any case, we think of a system as having a state, and we can calculate the different states of a system. And we know how to do that for very simple things like a particle in a box or an isotropic rotator or something like this. We know that in principle, we can calculate the wave function for such a system, and any property is defined by the wave function. So if we know if we know the state, that is to say we know the wave function of the system, then we can calculate the property. That's at the sort of microscopic level. Now we know that in principle, according to Schrödinger, we can describe the universe with a wave function. The universe is in some state. We can't generally calculate it, but in principle, that would be the physics approach to describing properties of things. Determine the wave function, determine the state. So our goal is to make a connection between quantum mechanics and bulk properties. So that's what we're doing. And we're going to leave aside the fact that for like a liter of water, you can't actually, everybody in Dr. Beadle's group would like to input this all into Gaussian and press the button on the computer, enter, and have the computer calculate the energy levels of a liter of water, but it can't be done. But in principle, it could be done, and that's the point. The problem then is that any macroscopic system has many, many different states that are accessible. And the assumption is that a property such as pressure or temperature must represent an average over many accessible states. So what's the connection? What's the kind of average we're talking about? So to approach this problem, or to approach, sort of early 20th century, some people worked hard. One of the most famous people was Gibbs. And you're familiar with Gibbs from Gibbs Free Energy. And Gibbs developed a conceptual approach based on something he called an ensemble. So we're going to talk about an ensemble. This was his method of thinking about this problem, making a connection. And maybe actually I should say before I bother writing the word ensemble, what we're trying to do is connect the idea of states, and maybe I should say quantum states, with thermodynamic properties. So an example would be energy states or energy levels. I won't worry about the distinction quite yet with the thermodynamic bulk energy. Okay, we have a limited number of symbols, so in general this would be the thermodynamic energy, and this would be energy state. That's our goal. So the ensemble. So an ensemble is a collection of systems. So maybe I should back up. A system is the physical stuff that we're interested in. So maybe the system is a milliliter of water. That's macroscopic. So the system is a macroscopic thing already. It's not one microscopic, 1 angstrom by 1 angstrom by 1 angstrom bit. It's macroscopic. The system is macroscopic. The ensemble is some supramacroscopic collection of systems. So let this be a system. We'll replicate the system many, many times. And the whole thing then is called an ensemble. So we're going to think about the ensemble. Now, in thermodynamics, we know that there are a limited number of properties that are sufficient to describe the thermodynamic state of a system. Pressure, temperature, for example. And if you remember back to the thermodynamic state functions, internal energy, enthalpy, Helmholtz free energy, Gibbs free energy, each of those has a set of natural variables. Those would be things that we can fix as constant. So for example, you might hold volume and temperature fixed. Or you might hold pressure instead, pressure and temperature fixed. So we will construct different kinds of ensembles according to thermodynamically which macroscopic variables we're defining. Okay. Different kinds of ensembles. Now the first one I want to discuss is actually pretty trivial, so it doesn't take long. One option we have is to hold fixed the volume and the energy. And the number of particles within the system. So we know that each system consists of some number of particles enclosed in a box. The box can be rigid, in that case it's volume we're holding fixed, or it can be flexible, in which case we might want to hold pressure fixed. So right now we're going to have a rigid box, so the system we'll have a fixed number of particles in each system, a particular volume, and particular energy. Okay. So in this case, every single system has the same number of particles and the same volume and the same energy. That's one way to construct. Okay. Later on, you can see we can relax this. If we let the walls be flexible, then we would hold pressure fixed and not volume. If we let the walls be permeable to heat, that is to diabatic, then energy can be transferred from one to the other. If we let the walls be permeable, we can let the particles pass back and forth, and we would hold the chemical potential constant instead of the number of particles. But to begin with, we'll start with NVE being constant. Okay. Well, that's probably the simplest one, because if these three things are constant, you could even take a step further back and simplify and say, let's suppose that the particles don't even talk to each other. There are no interparticle interactions. In that case, this would be like solving Schrödinger's equation for a particle in a box n times. And the energy levels would be really come from the solution to the particle in a box, which you could do, pretty not too hard. You'll find throughout the course that we begin with sort of simplest assumptions to get the lay of the land. And the simplest assumption is there are no interactions between particles. That really corresponds to the ideal to a perfect gas postulates that particles don't interact. So we're dealing with gaseous systems in the early part of the course, first with ideal ones, then we will allow for interparticle interactions. And only at the end will we enter the realm of condensed phases where the interactions are really important. Anyway, in principle, you could solve the Schrödinger's equation for this, you know, and it might not even be too hard in the simplest case. And if you did, you would find, of course, all the energies are the same. So that means all the energy levels must, you know, must be the same because we're holding energy constant. Now, I'm sure you're familiar with the concept of degeneracy from quantum mechanics. It's been held with here. It sometimes is the case that there are several states that happen to have the same energy. And if so, we call those states degenerate. So we got this ensemble. They may not, even though we're holding M, V, and E constant, they may not, all the systems may not be in precisely the same state, but they're all in degenerate states. Right? So So with NVE constant, we have omega degenerate states. Just as an aside, the text used this symbol once, and it also uses this symbol. And that's a little confusing, I think, because one can label the accessible energies as 1, 2, 3, and 4, and so on. And you can let 1, 2, 3, and 4 represent different states, or you can let 1, 2, 3, and 4 represent different energies. You know, energy level is state. And for most of the chapter, he lets the subscript represent a state, and there can be multiple states with the same value of the energy. But when he uses this symbol, he's obviously using the J to represent a level and not a state. So now a property, any particular property of the system would be defined by the state, right? The state defines the wave function. All properties come from the wave function. So if there's any property you want to know, what you would need to do is average over all of the omega degenerate states for this particular ensemble. Right? For each state, a given property may be different. So you have to average over them all. The property energy, of course, is the same. The problem. But some other property might be different from state to state, even though energy happens to be the same. So if you wanted to calculate the thermodynamic energy, you would have to average over all of the states, and then you'd have the thermodynamic energy. So then the question is, how do I perform this average? Are all states represented in equal proportion or differently in this average? And that's where we make an assumption. It's a postulate. The postulate is that there's no preference for one state over another. That's the postulate of equal a priori probability. So we need to calculate an average. So the property comes from some average over states. This is a postulate. It can't be proved. It's simply a postulate that all these states are equally probable. But it's a postulate that underlies the whole chapter, the whole book, in fact. And it seems to have worked out. you know. So all the thermodynamic properties we calculate from states using this approach based on this postulate have agreed with what you go and measure in reality. Okay. So it seems to work out. So there are several ways to think about this postulate of equal a priori probability. One is that you got an ensemble, all these different systems are here, NVE the same across all systems. Any system can be in any one of these omega states, just about degenerate. So if this ensemble is to represent that postulate, what we have to say is that each of these states is present an equal number of times in the ensemble. Ensemble can be any size. If it's of size omega, then each state's present once. If it's of size 10 omega, each state is present 10 times. But if so, then this ensemble represents really a huge supramacroscopic system. We just calculate an average with equal weighting of the states. One way to think about it. Another way to think about this is that you could just think about one particular system, let it be this one, and think of it as evolving in time. And what you would say is that over time, it's equally likely to be in any one of these states. Okay. So you can think about this postulate either for the, in terms of the ensemble or in terms of an individual state. Okay.
But don't some states have higher occupation numbers?
Yeah, no, yes, and I have to say yeah, because the answer is no here. But when we look at the next different kind of ensemble, you'll find that combinations of states for particular systems may be represented more often than other combinations. Mm-hmm. But the basic idea is quantum mechanics has no preference for one state over another. Equal a priori probability, very fundamental postulate. It's really the basis of it all. Just for the future, one thing you'll notice is we've talked about the number of particles in the let's define it. Let's A be the number of systems in the ensemble. So we've defined the number of systems, we've defined an energy, so we can speak about the system or the state, or the system or the ensemble. So for the ensemble, the jumping ahead. I'm good jumping ahead. I want to go on before I talk in those terms to the next kind of ensemble. Oh, by the way, this kind of ensemble where N, V, and E are constant is called the microcanonical. Ensemble. The microcanonical ensemble is composed of a huge number of systems, for each of which N, V, and E is constant the same. That defines the microcanonical ensemble. More common is where N, V, and temperature instead of energy, are constant. This is the canonical ensemble. Do you know what the word canonical means? That's weird. So it's standard. Standard, basically. The canon of English literature is the set of works in literature that are considered so important that everybody who studies literature reads them. That's the canon. for those into Christian theology, the canon of books of the Bible is fixed, it's a certain set. Some books are included in the Roman Catholic Bible and not in the Bibles others use, but by and large, it's a fixed canon that we all recognize. It's the standard. So canonical ensemble is the standard ensemble. So let's think about the canonical ensemble. How would we form this canonical ensemble? Because it helps to have a picture in our head. That's what I find anyway. We might do it this way. Start off with a set of systems, and you can prepare each system with a fixed N, V, and E, if you like, and put the whole thing in a bath with a fixed temperature. Okay. Each of these walls is diabatic, so it lets heat back and forth. The walls are rigid, so V is constant. And you prepare this so there's the same number of particles in each system. And now you just wait. Okay, you have to start initially with each system having some energy. It can be E, if you like. Now, since all of these walls are diabatic, over time, energy can pass back and forth between the walls. So we don't necessarily have a fixed, each system having the very same energy. It can fluctuate a little bit. After we let this equilibrate for a while, we remove the temperature bath and we make these walls, we place an adiabatic wall around the whole thing. And now what we have is the ensemble is isolated from the rest of the universe. So the ensemble itself you can think of as a huge microcanonical ensemble, right? But each of these systems may have a different energy. The energy of the ensemble is now fixed because we've isolated it, but the energies of the systems are free to change. In fact, maybe if I want to better distinguish the two, in this picture, the microcanonical ensemble, the systems are separated by adiabatic walls. No heat can pass back and forth. Here, the walls are diabatic. Heat can pass back and forth. Okay, this is the canonical ensemble.
When you say that the temperature is constant, you mean the temperature is constant for the whole ensemble, or is for each system the temperature constant? If you say that heat can pass through,
I mean the temperature for each system is the same. The temperature of each, because we're holding N, V, and T constant for the systems. Okay. But we're allowing heat to pass back and forth. So energy, we'll deal in the next chapter with fluctuations. But you can also think of an ensemble as a physically huge quantity of liquid, if you like, or gas, a huge quantity of gas. And you slice it up into systems. Okay. Each system itself is macroscopic, and the ensemble is also macroscopic. I mean, you have to get pretty small before you have to worry about quantum mechanical properties. You can get pretty small and you're still talking thermodynamics. Everything could be a continuum as far as you can tell. So you can think of this as a large volume of gas, and you slice it up like this. And a gas is at a particular temperature. You can place this huge quantity of gas in a thermal bath. And these partitions then are artificial. But you can imagine, in real life, of course, if there's no partition there, then particles can pass back and forth. That would not correspond to N constant, but it would be mu constant, chemical potential. Okay. But importantly, also energy can pass back and forth between these different regions of gas. And it's not the case that the energy is absolutely constant from here to there, right? But the temperature is constant, right? The temperature is a thermodynamic, it's a macroscopic property. Okay? So there will be slight fluctuations in the energies among the different systems that we have here. But when we speak about the macroscopic quantity temperature, it's a constant. Okay. We've fixed the temperature by doing this very physical thing, hands-on thing. Okay, it's really simple. It's like physical activity. Everything, the simpler it is, the better it's going to go. Same here. It's a very simple idea. Okay, very simple. What we're doing, by the way, is it's a thought experiment like Einstein did, right? You can't actually do this. And you can't actually calculate, we can't constrain the quantum mechanical energy levels of macroscopic systems, but we can do this thought experiment. And we're going through the thought experiment. Okay? So now we need to start talking about the states. We know that we can label the states, the quantum states, for the system. To each state is accessible, to each system is accessible some set of quantum states. And it's the same set for each system in this ensemble. And so we can label them 1, 2, 3, 4, 5, 6. Okay. So in this whole ensemble, suppose that we have A states, capital A states in the ensemble. Then at any point in time, we will have little a1 states. That's the number of states. I'm sorry, a1 is the number of systems in state 1. And A2 is the number of systems in state 2, etc. So the A sub j's are the distribution of the systems among the states. And it's going to be convenient to think of, instead of always talking about A1, A10, A15, let's just let the vector A represent this whole set. Okay. The book uses bold, I use this little arrow thing. So one thing we can say then is that if we sum up all the little A sub j's, we have to have the total number of systems in the ensemble. And we also know that if we sum up the product of the number of systems in a particular state times the energy of that state, we must have the total energy of the ensemble.
Capital A is number of systems in ensemble.
Oh, it's the number of systems. I said states, it's the number of systems. Thank you. Yeah, that's right. Okay, cool. Now there is one. Now, the principle of equal a priori probabilities applies, but there is a subtlety. There's more than one way to achieve a given distribution, and a given distribution of states. And so when we calculate a property, of course, we're going to average over all the states in all the systems in the ensemble. That means we're going to have to average over the distributions, right? And you might think offhand, well, we just treat each distribution the same. But it turns out that there's more than one way to achieve a given distribution, or more than one way to realize a given distribution. Some distributions have more ways of more realizations than others. So we have to be careful with the weighting. And that's really what I think you were getting at.
Hmm.
So we're going to define W for a given distribution as the number of ways to realize, or the number of realizations of distribution A.
It made sense to me in this example, didn't make sense to me in the prior. Like whenever, because they discussed it twice, when they discussed it,
Mhm.
talking about the canonical ensemble, it made perfect sense.
Okay. Okay, cool. I want to make this really concretely clear. So let's think about a particular distribution. I'm just going to choose the one I set up here. Suppose we have a small ensemble, and let's let the number of systems be 4, and let's let the total energy be 8. Units don't matter. Okay. Let's say that we have three different accessible energy states, or non-degenerate energy levels. It's just not worried about degeneracy. So we can have energy 1, energy 2, or energy 3. Okay. And let's suppose that the distribution of energy is that we have one system in state with energy 1, two systems. Is that the one I want? Yeah, two systems with energy 2 and one system with energy 3. Okay. So that's fine. Then you can see, by the way, A sub j, E sub j is 1 here, 4 here, 3 times 1 is 3 here, so that the sum over those is 8, and as we said. Okay. Now let's write out some possibilities. Here's that's our ensemble now, and so here we have the 4 systems in the ensemble, and this is one way to achieve the distribution 1, 2, 1. Here's another way to achieve the distribution 1, 2, 1. Etc. So each of these is a different realization. A different realization of the same distribution. How many realizations are there? Yeah, I mean, so that would simply be the polynomial distribution that we saw before. Okay. So in this case, the number of distributions is going to be A divided by the product over J of 8. Okay, or so in this case it's going to be 4 divided by 1 factorial, 2 factorial, 1 factorial, right? Which is 12. Right. Okay. Now let's think of another way to be consistent with these two constraints right here, and just use a different color. I could also, let's see,
3-1.
I could say 2, 0, 2, right? 2 plus 0 plus 2 is 4. 2 times 3 is 6, plus 2 times 1 is 8. So we still satisfy our constraints, no problem. Now, how many ways are there to achieve this distribution? 4 factorial over 2 factorial, 0 factorial, 2 factorial, which is 6. Okay. So, so this number is our W of the particular distribution we're talking about. So W is 6 for one particular distribution, but it's 12 for this other distribution. Yeah. So when we calculate the properties of systems, we need to average over all the different states the system could be in. Right? So we have a property that's defined by a state, but the system can be in many different states. So we have to average over all the different possible states. So we need to know the probability that we're going to be in any particular state. And that probability will be the probability that we're is the this is the this is the A sub j. So that's the, for a particular distribution, it's the number of states. Yeah, it's the number of state j's that happen to be present in this distribution. Divided by the total number of states in the system. Right? This is the total. This is the number of states, state j's, and that's the total number of states. Thing is that for each distribution, there's going to be a different number of a different A, right? So what we need is the average value. But remember, each distribution has a different weight depending on what the distribution is. So not all distributions are the same. So how do we think about that?
So the distribution is the occupation number.
The distribution, oh, that's a good word. So that you can call this the occupation number. That's right, that's the occupation number. So this is the average value of the occupation number divided by the total of states, or the total number of systems in the ensemble. However, in each distribution, the occupation number is fixed for a given distribution, but there are various, each distribution may be realized in W different ways, depends on the distribution. Okay. So this is not an equally weighted over, so each distribution may be weighted differently. So this becomes, man, I gotta, that's our P sub j. Okay. So I use the vector for A here because it's a vector. Okay. That's where we have to begin. That's what we got to figure out. If we can figure out the P sub j's, we're done because we can calculate the value of a property in each state. So we just got to figure out the probability of a given state. Okay. So that's what we have to work on. Now that looks pretty hard because we've got all these different distributions to deal with. Okay.
Is there, I'm sorry, is there an equation to figure out all possible distributions, or you have to sit there and just look at, you know, because I can think of another arrangement of possible, you know, distributions for the energies, but is there a simple way to make sure?
You don't have to write them out. You don't have to,
No.
you don't have to draw them out. You just have to remember this formula. Right, so once you have the occupation numbers for each distribution, for a given distribution, you figure out its weight. Right, that's W. Okay, you don't have to draw the pictures out, you just have to write down how many, what are the distribution numbers, what are the occupation numbers defining your distribution. And from the occupation numbers, you figure out the weight. Okay. Now, we saw last time that
Right.
if you remember last time, we don't, I should have tested these like I did last time. Last time we talked in particular about the binomial distribution, which means, of course, we have n objects. In one of them are in one bin, in two of them are in some other bin, right? And we talked about the different ways we can arrange them and so forth. And we saw that let vertical is going to be W. It's going to be the number of ways to achieve, or to realize a given distribution. And you can write W as a function of n1 for a given n. Right? And we saw for, let's write the n down here, n1 down here. The maximum value of n1, of course, is n. N2 is 0, n1 is n, biggest n1. And we saw that this is peaked, highly peaked, around n over 2. Okay. So you're going to have the most ways to realize a distribution for the equal n1 equals n2 distribution. That carries over to the polynomial distribution. The most ways to achieve a distribution will be with equal numbers in each bin. Okay. And the bigger you make your sample, capital N, the more peaked this becomes. And when we saw last time, if we're talking about Avogadro's number or something, we saw that the range here is from 0 to 10 to the 24th, and the width of this is 12 orders of magnitude smaller.